Good morning. Welcome to online section. Today we will see that application of Gauss law at thin spherical cell. Before, dear student, you can also subscribe my YouTube channel, like, comment, share it. Don't forget click the bell buttons. Let us start our class today. Today motivation taught by Dr. ABJ Abdul Kalam. He says that success is when your signature changes to autograph. I repeat, keep your mind, dear students, success is when your signature changes to autograph. Okay, dear student, let us start our class today. Today we will see that thin spherical cell. It is two methods. One, thin spherical cell field at outside the cell, and thin spherical cell field at inside the cell. First, we are going to discussing thin spherical cell electric field at outside the cell. You know Gauss law, and the situation has spherical symmetry. The field at any point P outside or inside can depend only on R, the radius distance from the center of the cell to the point, and must be the radial. It is along the radius vector. You know that you can see image of presentations. Consider a thin spherical cell S of radius of R, and let the thin spherical cell be uniformly charged with a positive charge Q, and the surface charge density sigma equal to Q divided by A, where Q is a electric charge, where A is the surface area of the sphere. And also you can see the image, electric field due to the uniformly charged thin spherical cell has a spherical symmetry, and the electric field strength at any point is equal in the magnitude and is directly radially outward. You know very well, applying the Gauss law, an expression for electric field strength at a point P1 outside the spherical cell at a distance x from the cell can be derived. You know the image of diagrams. A point B outside the cell from the Gauss law equal to closed integral A vector dot ds vector equal to Q divided by epsilon naught. Yes, students, you know that clearly, since electric field and ds vector are in the same directions, so that's why we can write for equal to closed integral of E vector dx equal to Q divided by epsilon naught, and also we substitute the value of area, sigma equal to ts equal to 4 by r squared. So we substitute, we will get that E equal to 4 by r squared equal to Q divided by epsilon naught. We interchange the equations and also we modify. Dear students, we will get E equal to Q divided by 4 by epsilon naught r squared, since Q equal to sigma into 4 by r squared. So we can modify E vector equal to, or electric field equal to, sigma r squared divided by epsilon naught r squared. and electric field due to the uniformly charged thin spherical cell at a point outside the cell is such as the whole charge were concentrated at the center of the cell. The electric field that gives electric field strength due to the uniformly charged thin spherical cell at a point of P1, which is a distance x from the spherical cell. If the charge q greater than 0, just note on that, dear students, if the charge q greater than 0, the electric field is directed outward from the center of the cell. Dear student, it's very important, just note on that. If the charge q greater than 0, the electric field is directed outward from the center of the cell, and another hand, if q less than 0, the electric field is directed inwards. Thus, for any point P1 outside the uniformly charged cell, the electric field T2 the cell as if the entire charge and the cell is concentrated at its center. Okay, and next we are going to discussing about that thin spherical shell filled inside the cell. It is easy, you know that clearly. For this one, the image of diagrams, you can see the point B inside the cell. The Gaussian surface is against the sphere through P center at O. Remember, I repeat, the Gaussian surface is again a sphere through P centered at O. The flux through the Gaussian surface calculated as before is E equal to 4 by R squared. As usual, what you calculated field outside the cell, same as like the flux through the Gaussian surface, the calculated as before is E equal to 4 by R squared. However, in this case, you know Gauss law, the Gauss theorem says that in this case Gaussian surface enclosed no charge. You know clearly that one. That's why the Gauss law then give us E equal to 4 by R squared equal to 0. That's why we'll get that electric field equal to 0. That is R less than greater than of R. You know that R less than capital of R. That is the field due to the uniformly charged thin spherical cell is 0 at all point inside the cell. So dear students, keep your mind, the field due to the uniformly charged thin cell is 0 at all points inside the cell, and the important result is a direct consequence of Gauss law which follow from Coulomb's law, and it is the experimental verification of the result confirms the 1 by R squared difference in Coulomb's law. Okay, I hope you well. Okay, peace be with you. Thank you.